Hello friends, good morning. Today we are going to start with our next chapter, that is next topic, that is about the sign conventions of enthalpy. Then we are going to come with the heat capacity today. So these two main important points we are going to discuss today in our discussion, right? I will go in brief about what we have done in the previous part. So see, we have seen about the 0th law of thermodynamics. Then we have seen about the first law of thermodynamics, right? Then we have come to the different, that is internal energy we have discussed in detail. Then we have discussed in detail about the enthalpy, and then we have come in detail about the what are the state functions. Clear? Now, as we have discussed yesterday about enthalpy in detail, today we are going to continue its next part only. Right? Yesterday we didn't discuss anything about any relationships of the enthalpy. Clear? Now today we are going to first discuss about what are the sign conventions of enthalpy. As I have told you yesterday only that enthalpy, internal energy, these are the state functions. Right? It does mean that enthalpy or the internal energy, as it is only as E or H, that is alone enthalpy, alone internal energy, we cannot measure. We have to express it in terms of only delta E or delta H. Is it clear? Right? It does mean that there are some sign conventions as they were for yesterday, as we have seen about the work done, about the internal energy, about the heat, that is Q. Right? We have seen the sign conventions for these yesterday. Similar to that, today we are going to discuss about the sign conventions of the enthalpy. Now, the enthalpy, as I will repeat again, it is what? It can be defined as the algebraic sum of internal energy and the product of pressure and volume. So, what will be its mathematical expression? Its mathematical expression will be H is equal to E plus PV, isn't it? H is equal to E plus PV. Now, as H is equal to E plus PV, as yesterday only I have told you that, and today again I am repeating again and again that it is to be represented as delta H only, right? Now, we can say that delta H is what? Obviously, delta H is equal to H2 minus H1, right? Now, for any chemical reaction, let us say that H2 stands for the enthalpy of the products, right? What is H2? H2 is enthalpy of products. What will be the H1 then? H1 is enthalpy of reactants. Clear? Again I will repeat, H2 as the enthalpy of the products, H1 is the enthalpy of the reactants. Now, for the any process or for any type of chemical reaction, delta H reaction will be what? Delta H reaction will be equal to enthalpy of products, that is H2 minus H1, that is enthalpy of reactants. Now, let us now discuss the discussion about the sign conventions of the enthalpy, right? Now, what are the sign conventions? When delta H, the value of delta H is negative. When it will be negative, it's very common sense, right? Because as delta H is H2 minus H1, obviously when H2 is greater than H1, delta H will be positive, right? What is when H2 is greater than H1, delta H is positive. When delta H is negative, H2 is lesser than H1. H2 is lesser than H1. When H2 is greater than H1, delta H is positive. When H2 is lesser than H1, delta H is negative, isn't it? Now, it does mean that when the enthalpy of the products is greater than the enthalpy of the reactants, then the enthalpy of the reaction comes out to be negative, right? When the enthalpy of the products is lesser than the enthalpy of the reactants, delta H is positive. Is it clear? It's very simple. By common sense only we can correlate the sign conventions of delta H. समजते है सगळ्यांना, right? Next. Now we will discuss about some relationships over here. What does mean by the relation? What is the relationship between delta H and delta E for the isochoric process? Right? Now for what? We will discuss for isochoric process. Now all of you very well know of that. What does mean by isochoric process? What is isochoric process? Isochoric process is the process, again I am repeating over here. Isochoric process is the process where volume remains constant, right? Now when volume is remaining constant, it does mean that, right? Now for isochoric process, we will write again delta H is equal to delta E plus P delta V. What is it? This is according to the definition of enthalpy. What is definition of enthalpy? H is equal to E plus PV, right? Now dear students, don't get confused at all. हा चॅप्टर आहे ना बऱ्याच मॅथमॅटिकल एक्सप्रेशन्सचा सुद्धा आहे हां, पण ह्या मॅथमॅटिकल एक्सप्रेशन्स ह्या सगळ्या कशात त्याच्या प्रत्येकाला बेस आहे आणि हा बेस तुमचा भरपूर क्लिअर झालेला आहे असं मला वाटतं आता. सो नुसत्या डेफिनेशनवरून सुद्धा आपण आता इक्वेशन्स तयार करू शकतो आणि जसं जसे आपले कन्सेप्ट क्लिअर होत जातात तसं तसे इक्वेशन वी कॅन राईट ऑन आवर ओन. आपण स्वतःच्या मनाने सुद्धा इक्वेशन लिहू शकतो आणि तेच करायचं हवं आहे. ठीक आहे. तर डेल्टा एच इज इक्वल टू व्हॉट? डेल्टा ई प्लस पी डेल्टा व्ही, राईट. आता मला सांगा व्हॉट इज आयसोकोरिक प्रोसेस? व्हॉल्यूम रिमेन्स कॉन्स्टंट. It does mean by delta V is 0. Obviously this part goes out. What you will get? Delta H is equal to delta E. Clear? So simply for isochoric processes, the relationship between delta H and delta E is that delta H is equal to delta E when volume remains constant. Got it? Now what will be that for isobaric process? Now for isobaric process, आता isobaric process मध्ये आपल्याला माहिती आहे what is constant? Pressure is constant, right? Again I will write the same equation as delta H is equal to delta E plus P delta V. Here again what is 0? P is 0. It means that this term goes out. This is equal to 0, right? So delta H is equal to again delta E. But here since it is an isobaric process, we can write instead of delta E, it is what? Delta H will be equal to the heat only at constant pressure, right? And hence it can be represented as Q with constant pressure P. Is it clear to you? Is it clear to everyone? Right? So what is that? For isobaric processes, delta H is equal to QP. Now we will go to the next point. What's that? Now a new term we are going to start today, that is heat capacity. What is this? The heat capacity, it is again one thermodynamic property. Clear? Now how it is defined? What is heat capacity? Heat capacity is defined as the amount of heat required in calories to raise the temperature of the system through 1 degree centigrade under the given set of conditions. Again I will repeat, what is heat capacity? Heat capacity is defined as the amount of heat required to raise the temperature through 1 degree centigrade of the system under the given set of conditions. Is it clear? So what is heat capacity? Heat capacity is the amount of heat required in calories. Amount of heat required in calories by the system for raising the temperature through 1 degree centigrade. What does it mean? It means that heat capacity depends upon the temperature. It is a thermodynamic property which is dependent upon the temperature. Now dear students, properly keep in mind, heat capacity as it is temperature dependent, it is also mass dependent. And while explaining the extensive and intensive property in my first video, I have told you that the heat capacity or the heat is enthalpy is an extensive property. Similarly, heat capacity is also an extensive property as it is a mass dependent. It depends upon the quantity, it depends upon the mass. It does mean that heat capacity is the extensive property. Clear? So, as heat capacity is a is the amount of heat required in calories to raise the temperature through 1 degree centigrade, isn't it? It is denoted by capital C, right? So, heat capacity is denoted by capital C. Now, heat capacity we can mathematically express it as Q upon T2 minus T1, where T2 is the temperature of final state of the system and T1 is the temperature of the initial state of the system. So, we can also write it as C is equal to dq by dt. What is that? C is equal to dq by dt. This one is very important equation, mathematical expression for the heat capacity. What is that? C is equal to dq by dt. Why? Because as it is directly, as the heat capacity is directly dependent upon the mass, as it is directly dependent upon the temperature, we can write it as C is equal to dq by dt, that is the change in the mass and change in the temperature directly affects the heat capacity, right? Now, this heat capacity is generally represented by two ways, right? What is that? That is about the molar heat capacity at constant volume and molar heat capacity at the constant pressure. Because in chemistry, in the thermodynamics itself, heat capacity is generally expressed in the form of molar heat capacity, right? Now, first of all, we will discuss in brief about the molar heat capacity. Clear? What is that? The molar heat capacity is defined as the amount of heat required to raise the temperature of the system containing 1 mole of the substance, right, through 1 degree centigrade. Under the given set of conditions, such heat capacity is called as a molar heat capacity. So, molar heat capacity, I will repeat, what is that? It is the amount of heat required to raise the temperature through 1 degree centigrade, and that is the for 1 mole of the substance, present in the system, that capacity is called as the molar heat capacity. Again, I will repeat, molar heat capacity is the amount of heat required to raise the temperature through 1 degree centigrade of the system containing 1 mole of the substance under the given set of conditions. I think it is clear now as I have repeated. The molar heat capacity, it itself is to be represented as the molar heat capacity at constant pressure and molar heat capacity at constant volume. Clear? Now, what is the molar heat capacity? Let us see. It is represented as Cp. Cp and Cv. What is this? Cp is molar heat capacity at constant pressure and Cv is molar heat capacity at constant volume. What are these? Simply, Cp can be defined as the amount of heat required in calories to raise the temperature through 1 degree centigrade of 1 mole of the gas, of 1 mole of the substance present in the system through 1 degree centigrade under the given set of conditions, that is at constant pressure. Similarly, Cv can also be defined as the amount of heat required to raise the temperature through 1 degree centigrade of 1 mole of the gas or 1 mole of the substance through 1 degree centigrade at constant volume. Is it clear? So, this is all about the Cp and Cv definitions. Now how they are mathematically expressed? Cp is generally expressed equal to dq by dt at constant pressure, and that is equal to dE by dt. Cv is equal to, now let us see what is Cv. Cv is the heat capacity at constant volume. Cv is equal to dE by dt, as this is equal to dq by dt at constant volume, right? Cv, that is heat capacity at constant volume, that comes out to be dq by dt, that is the heat capacity at constant volume, that is dE by dt, right? Cp is equal to dq by dt, that is dE upon dt, as this is also dE upon dt, but at constant pressure we represented it as dq by dt. Is it clear to you? Don't get confused over here, right? This is little bit confusing, but both are what? The change in heat with respect to time, with respect to temperature, change in heat with respect to the temperature. Now further we are going to discuss here about the Mayer's relationship. What is that? Mayer's relationship. Mayer's relationship tells us about the relationship between the Cp and Cv, right? Now what are these Cp and Cv that we have discussed till now? Clear? Now let us come back to our equation, mathematical expression for the enthalpy. Let me know what is that. H is equal to E plus Pv, isn't it? So many times I have repeated over here. Enthalpy is equal to energy, internal energy plus PV, that is pressure volume, right? Now let us take the differential of both with respect to the temperature. What is it? dH by dt is equal to dE by dt plus PdV by dt. Am I right? dH by dt is equal to dE by dt plus PdV by dt, isn't it? Now dH by dt, that will be equal to what? That is Cp. dE by dt, we can replace dE by dt as dE by dt as Cp, right? What is P? We will write it this term as it is, PdV by dt. Clear? Now we will write the ideal gas equation, right? For 1 mole of gas, all of we know that PV is equal to what? PV is equal to RT, correct? Therefore PdV by dt is equal to what? R dt, RT upon dt, right? Now what is R? Now from here we can say R is equal to, as R is constant, we can say that R is equal to dV by dt, R is equal to dV by dt PdP, right? R is equal to dV by dt upon dP by P. So we will replace over here dV by dt by R. So how this term whole will be equal to R, and hence Cp is equal to Cv plus R. Clear? So what does it mean? It means that Cp minus Cv is equal to R. So what is that? Cp minus Cv is equal to R. So this relationship is called as the Mayer's relationship. What's that? Cp minus Cv is equal to R. So Cp minus Cv is equal to R is given by the Mayer's, and hence on its name the relationship is called as Mayer's relationship. What is R? Here R stands for the gas constant. Clear? So I think with this today's our discussion, we have discussed about the sign conventions of the enthalpy. Then we have discussed about the relationship between the delta H and delta E for isobaric process and for isochoric processes also. Then we came to the new point of the today's lecture, that is about the heat capacity. We have discussed in detail about what is heat capacity. Then we have discussed about the molar heat capacity, and then came we to the Mayer's relationship and its derivation. I think all of these points are properly understood to you and you are clear with all of the concepts, right? So we will stop over here with the today's lecture. We are going to meet again in the next part.